Hello everyone and welcome to this lecture where we'll be introducing you to MANOVA. So by the end of this session in the directed activities you should have a good idea of when and why you would use MANOVA. So that is in relation to research design, research questions, the kinds of data and so on. You should also have some insight of how MANOVA works, what it can tell you, how you can probe initial findings further, and also some ideas of how to handle messy data. We'll also be thinking about what's the minimum information you'd need to report from a MANOVA, and how to do that in relation to APA recommendations. And we'd also look at some of the strengths and limitations of MANOVA as an approach. So the example I'm going to be using today is one that I've worked on. So I was a co-author on this paper, and it's something, if you've looked at the factor analysis lecture already, you'll be familiar with it. And it's mainly because I can use my experience of doing that analysis to kind of highlight some of the issues as we're going through. So I thought it would be useful to give you that perspective on what it was actually like to do that with real world data and to deal with some of the issues and so on. So if I just show you this paper now, there's a link to it that goes through our library subscriptions. So once you've followed that link, it'll ask you to sign in, and then you should be able to access the paper. So this is the paper, and the aspect of the research I'm going to be looking at is about testing the convergent validity of this new measure that we were developing. So the measure was the nature of the paper was measurement development, and we wanted to see whether a questionnaire that was initially developed for use for professional nurses, so nurses who already qualified, to explore their approach to evidence-based practice, which is an approach to medicine and healthcare where you use best, most reliable evidence to inform your practice. So using research evidence, for example, to inform your practice. We wanted to explore whether a measure that was designed to be used with professional qualified nurses could be used with student nurses, or whether it would need to be adapted. And also what we found is that it did need to be adapted. And then we wanted to test how good it was at differentiating between people and so on. So what I'm going to be drawing on is the use of a one-way MANOVA where we looked at the differences in these profiles of evidence-based practice of students in their first, second and third year of their degrees. So that's what I'm going to be drawing on. So what is MANOVA? Okay, so MANOVA, the term stands for multivariate analysis of variance. And so instantly what you can see from that is at the heart of it, it's based on analysis of variance. It's an expansion of that. It's a development of analysis of variance. So it's still considered a sort of test of difference. It's a very crude way of kind of differentiating between different approaches, but people often refer to tests of difference as opposed to tests of relationship, like correlation and regression. So you can think of it in a similar way as to analysis of variance. In some places, it makes some of the parametric assumptions that we're used to seeing, in others it doesn't, and we'll come to those in a little bit. What it can be used for is if you have an independent variable that has that's categorical. So if your independent variable has two or more groups or conditions, then MANOVA is something that you can use. But it can also be used where you have more than one independent variable as well. So both of your independent variables need to be categorical, but you could have two categorical variables, each with two or more conditions. The difference is to MANOVA in comparison to ANOVA is that it handles more than one dependent variable at a time. So it can be a very useful test. What you might be thinking then is, well, why wouldn't I just do lots of ANOVAs separately for each of the dependent variables? Why couldn't I just take that approach? The answer is that you could. It depends on the situation you're faced with. But what is one of the advantages of MANOVA is that by looking at your dependent variables simultaneously, one of the arguments is that you can reduce the risk of committing a type 1 error because you can slim down the number of initial analyses you have to do. So the way that MANOVA works is that in its initial statistical test result that it provides you with, that acts as a sort of cap for the type 1 error, because if you find an effect at that level, then it would suggest that there is something genuine going on when you break down your analyses even further. But there are issues with that argument, and we'll look at some of those in a little bit. But it can be a more kind of, not straightforward, but a more streamlined approach than just doing lots of separate ANOVAs. It gives you somewhere to start, if that makes sense. What it has to have are, if you're going to look at these dependent variables simultaneously, then they need to be theoretically linked constructs. It needs to make sense that you're going to look at them together. So if you've got a series of hypotheses that each addresses a separate dependent variable, and though in a paper, those things aren't really that kind of theoretically linked, it doesn't make sense to consider them all together, then maybe MANOVA wouldn't be the most appropriate. But for example, if we're looking at a piece of research and we want to look at something called subjective well-being, there's an argument that subjective well-being is the overall construct, and that's made up of things like cognitive well-being, emotional well-being, and social well-being. Now, each of those different types of well-being might be measured using a different type of questionnaire. And so what you might want to do is use MANOVA to initially look at, when we bring all of those 3 different questionnaires together, and we look at the differences between our groups, perhaps males and females, for example, just to illustrate. Do we find a difference when we consider them all together as this sort of subjective well-being? And if so, when we break it down further, is it because we see a difference on cognitive well-being, on emotional well-being, on social well-being, on only 2 of those, or only 1 of those dependent variables? What's going on? What aspect of subjective well-being do we find the differences on? And so it makes sense then to run a MANOVA, because what the MANOVA actually initially does is it takes these 3 initially separate dependent variables, and it looks at the relationships between those, and it constructs essentially a new dependent variable, which would be kind of reflective of our idea of that subjective well-being, of the kind of the whole that these 3 things make up. And then it tests the difference between the 2 groups on that. And then with the MANOVA, what we can do is break it down further, and so on. But they have to be theoretically linked. So, for example, looking at the example paper, the measure of evidence-based practice that we were doing was used to how we described it as to look at to students' practice, evidence-based practice profiles. And that was made up of self-reported frequency of use, their attitudes towards evidence-based practice, and different aspects of their knowledge and skills. So their knowledge and skills in applying and sharing information and evidence, and their knowledge and skills in retrieving and evaluating evidence. So all of these things fit together in this kind of theoretical way. We would expect all these things to be related to each other to some degree, and we would expect that they provide us with this idea of this overall profile of evidence-based practice. And so in that example, it made sense to do a MANOVA, to look at the differences in students in their first, second and third years on these profiles. And then if we did find an overall difference, what was it on? Was it on their frequency of use? Was it on their skills and their knowledge and in applying and sharing or retrieving and evaluating information and so on? So MANOVA is useful when we want to look at the way that these dependent variables fit together, and when treated as a whole, do we find something going on, a difference between our groups, or a difference potentially in time points, for example. So what is MANOVA? Okay, we're going to look at this in a bit more detail. As I've already said, it can be considered an extension of ANOVA, But it's and it is a sort of Dabachnik and Fiddle refer to it as a special case of the general linear model. And if you think back to ANOVA, what ANOVA does is it allows you to test the null hypothesis that the means of different groups or conditions are equal. So if the null hypothesis is correct, we're saying that there be no difference in the means between each of our groups or conditions. Now in MANOVA, that's slightly different. What it's actually testing is the null hypothesis that the mean vectors are equal. So actually that's linear combinations of scores across the dependent variables, so how they come together, and then it breaks it down, as you'll see later, and we look at our univariate effects, which are exactly the same as actually what you'll see is potentially just a series of ANOVAs that has been run then separately for each dependent variable, but we'll come on to that in a little bit. So what you have for a MANOVA is you have, again, an omnibus test. If you have more than two groups, all it does, or two conditions, all it does is tell you that there's a significant difference in the mean vectors somewhere between those groups. But if you've got three groups, we wouldn't know if there's a difference between two of them or three or what was going on. You'd have to do further testing. And then, so the multivariate test is the thing where we look at our dependent variables all as one lump, as one big new dependent variable all together. So that would be the example of when we look at the difference overall on evidence-based practice profile or overall on subjective well-being. And then usually the approach is that if we find that, then it warrants us looking in closer detail at each dependent variable separately. And actually then what we have are a series of univariate tests. So univariate is where we're looking at a single dependent variable in this context. And again, it's an omnibus test. So if we have more than three groups, as we did in the example paper, we had students in their first, second, and third years, then the issue is that we would just know that there's a difference somewhere on a dependent variable between the three groups. Not if it was between each of the three groups or only two of them, what was going on. We would have to do further testing again. And so what you'll find is a MANOVA works in quite a sequential way, which if you follow the steps, it makes it a lot easier to understand. Otherwise, it can be a little bit overwhelming when you actually get the output of a MANOVA, as you'll probably find out. But it's to remember that it breaks down in this way. You start off looking at the overall big effect, and then you break it down into ever smaller effects to really pinpoint where those differences are happening. So in terms of terminology, now it's sometimes you'll see it's referred to in quite a similar way to ANOVA, but there are some key differences. And the issue is that in an ANOVA, we know that you can only ever be handling one dependent variable. So in MANOVA, the way that people sometimes describe the MANOVA, it actually includes information about how many dependent variables we have. So if you see someone talking about a one-way between groups MANOVA, or two-way between groups MANOVA, or three-way between groups MANOVA, then that's usually where they're talking about the number of independent variables and not necessarily telling you anything about the dependent variables. But if you see someone as written, they did a 2x3 MANOVA, what that might suggest is that they have an independent variable with two levels and then three dependent variables, or it could actually be that you have two independent variables and three dependent variables. So actually it can be really confusing. So what I would say is if you're going to write about doing a MANOVA yourself, that you talk about it as one way between groups MANOVA with three dependent variables, for example, something like that. So it's really clear and there's no confusion to the reader. But you'll see that actually sometimes people use very different ways to describe the MANOVA, and it's not always that helpful. So just think about how clear it is to your reader when you're describing a MANOVA. So, for example, there in this example we had, I might use the terms a one-way between groups MANOVA because in the example paper, we only had the one independent variable, which was year of study that the students were in doing their degree. Or you could potentially call it a 3x4 between groups MANOVA, because I had 3 levels of my IV and I had 4 dependent variables. And so the between groups just tells you that each person appeared in only one level of the IV, one of the 3 levels. So they were either in their first year of studies, either in their second year of studies, or in their third year of studies. They didn't. It wasn't a longitudinal project in this example. It wasn't measuring someone at each time point. It was that at the as a snapshot, they were either in their first, their second, or their third year. But as I said, you can get a sense of how confusing it is to describe a MANOVA sometimes. So I would just be really clear how many independent variables you have and how many levels and how many dependent variables you have. So in this example paper, we've already kind of alluded to it, but the 4 dependent variables were the frequency of use of evidence-based practice, their attitudes towards evidence-based practice, the knowledge and skills, their self-reported knowledge and skills in retrieving and evaluating evidence, and in applying and sharing evidence. So there are these 4 dependent variables, and actually they use different scales to kind of collect the data. Typically we analyse it using a mean score for each of the subscales, but not necessarily. Sometimes authors using the scale will use a total. But so it doesn't necessarily matter if your dependent variables are measured on different scales, as long as they're all continuous. Okay, your dependent variables in a MANOVA have to be scale level, but we'll come on to that in a little bit. So we're starting to get a sense of what MANOVA is and when you might use it. But to kind of really illustrate all the different approaches, all the different, research questions that it can help you with, I've put together some of these that I've kind of taken from examples in the literature, so I've kind of paraphrased them. So the first one you're familiar with, and that's the one from the example paper that I've been drawing on. Can a new measure of evidence-based practice detect differences in the evidence-based practice profiles of nursing degree students in different years of study? So we wanted to know if it could identify differences between students in those 3 years on each of the 4 dependent variables, or perhaps only some of them, and what that might be. But other examples from the literature, and I've actually got links to these papers on the next slide, are does students' academic level and type of course delivery mode, so kind of online or blended, influence students' use of 8 motivational regulation strategies, and I should say 3 types of engagement. Do people process multisensory stimuli and distractors at the level of features or as a configuration of features, depending on attention? So whether it's something they were directly attending to or something outside of their direct attention. So that's probably for any fan of cognitive psychology, that's a really good paper. To what extent can lay people, in comparison to nurses with experience of supporting older people with dementia, can they rate the pain behaviours observed in videos depicting patients with dementia, which were portrayed by actors, accurately? So using these standardised measures, they wanted to know in this piece of research, can standardised measures that have been used, that have been developed for use with qualified nurses, well, actually, can lay people who perhaps live with or support people with dementia, can they be used to the same degree? So identifying whether someone is showing pain or no pain to the same degree, the accuracy of that, but also if someone is demonstrating pain, the degree to which lay people can use these tools to identify different levels of pain, so from no pain up to severe pain. And finally, they're more of a kind of a sports and exercise and mental health kind of topic area and health psychology area. But to what extent does a 12-week group physical exercise intervention for patients with panic disorder, how does that perform on 3 primary outcome measures relating to mobility, agoraphobia, and body sensations in comparison to the same length group CBT intervention. So again, kind of an intervention study there. And actually, each of those example questions match up to these different links here. So the between groups, repeated measures, and mixed methods. So those terms are things that you're going to be familiar with from MANOVA. So between groups means that each participant only appears in one level of your IV. If you've got more than one IV, they only appear in one subgroup when you look at those two IVs together. Repeated measures is that actually each participant appears in every level of your IV or IVs. So if it's a condition, they take part in before, intervention 1, then they take part in intervention 2, and so on. Mixed methods is where you've got an element of the two. So it may be the difference between the two groups and across different conditions, different severities, or so on. And so those are some examples of terms that you have encountered already. Now there is an additional type of MANOVA which you just don't get, that doesn't have a corresponding ANOVA example. And this is what's called doubly multivariate. And that's where, in particular, if you are taking multiple measures of the of multiple different types of dependent variable at multiple time points, then this approach is quite useful. And actually, it can avoid some of the assumptions that you would encounter and have to satisfy if you were doing a mixed methods, a straightforward mixed methods MANOVA. And that's where you treat time not as an independent variable as such, but as a type of measure. So it recognises that you've got your first dependent variable at time point 1, at time point 2, at time point 3, and so on. And so it doesn't make some of the same assumptions that it would do if you were using a straightforward mixed methods approach. And so it can be useful to know about. Unfortunately, because it's less commonly used, there are fewer guidance on using it. But if you have a look at the Tabachnik and Fiddle book, on their chapter on MANOVA and MANCOVA, so MANCOVA is multivariate analysis of covariance, but they talk through doubly multivariate MANOVA, and they give an example, so it's really good. But there's an example from the literature of a doubly multivariate MANOVA as well. It's only a certain set of variables that come together, a scenario, particular scenarios where you would use that, particularly if it's like a longitudinal study that you want to try and look at. So you've got different time points and the same people in each time point. Then that is an option to know about, but most of the time we don't need to use it. Oh, sorry, I should say as well. So those are the different approaches. And as we've looked at in the other lectures in this series, it actually MANOVA would fit really well with cross-sectional designs, which is the example from the paper that I co-authored, quasi-experimental designs and experimental. So the repeated measures example is quite a heavy experimental design, and observational studies as well, and things like that. So it fits very well with a lot of quantitative or commonly used quantitative research designs. And like with anything, it just needs to have variables that are operationalized well, so they make sense how you've measured them, that you've measured them as reliable and accurate a way as possible, that you have tried to avoid issues with independence of observations where appropriate, and so on. But it can be used in a wide range of circumstances. So in terms of the data considerations, I've already talked about some of these. So the first one is that you have one or more independent variables and they are categorical. So your IVs have to be categorical. There are times where you can potentially have a continuous covariate included, but they become very challenging to do, and that's the same for ANCOVA, which is analysis of covariance. And I'd avoid those if you can. You would also need to have more than one dependent variable, and that must be continuous. So you'd need more than one dependent variable, and it has to be scale level, so either measured at the interval or ratio level. If you're including a time element, as I've already said, then it makes sense to use the doubly multivariate MANOVA because it doesn't make assumptions of sphericity. So that's something you should be aware of from the repeated measures ANOVA designs, and satisfying that assumption. And you can run into a range of problems when you're trying to do that with MANOVA, and so actually using a doubly multivariate MANOVA is where you can avoid some of those assumptions. So, as I've said earlier, it does make a number of assumptions about your data, parametric data assumptions, and this is that the data is normally distributed around each level of the IV or IVs and linear combinations of the DVs. Now, assessing this in practice, if you've got only a one-way MANOVA, then it can be fairly straightforward to do, but as soon as you have more than one independent variable, it starts to get more and more complicated to explore this. And so there's a move, initially the way that we would normally check the normality assumption might be with looking at the raw data in each group and each subgroup of your design for each dependent variable. But actually there's a move towards using the error in the model instead, just as we have done with ANOVA and just as we have done with regression. So following that same kind of approach, and particularly where you have complex designs, that can make things a lot more straightforward. We assume that the observations are independent in that your score on one of the dependent variables shouldn't be influencing my score and so on. And we assume as well there's no multicollinearity between the dependent variables. So in regression, we're worried about multicollinearity in the predictors. In MANOVA, we're worried about multicollinearity in dependent variables. And this is because if you have two dependent variables that are so highly related to each other, they're essentially the same thing measured twice, it massively reduces the power of your analysis, and it can create spurious results as well. So if you have dependent variables that are strongly correlated with each other, it's not a good idea to just use those in the analysis. It would make more sense to split your analysis up and look at them separately using separate ANOVAs than to try and do them in combination. But we'll look at that in a little bit later as well. It also makes an assumption about something called the equality of error covariance matrices, which is tested by something called Box's test. Now, whether or not this is a real problem, it depends. If you've got equal numbers of people in each group in your design or in each condition in your design, then it's not something to worry about. However, as soon as you have unequal groups sizes, it becomes a problem, and you've got to investigate it further to see if it's really problematic or if actually no, it's fine. So you have to go into a lot more depth, which is why you'd always suggest that you have both adequate sample size for each cell of the design, but that you recruit equally. I'll talk a little bit more about that on the next slide. So you need to have enough data in each cell of the design for it to run. So what that actually means in practice, there are two ways of thinking about it. The first is in terms of getting the MANOVA to actually run in the at all, in which case you have to have at least one more observation in each cell of your design, so each subgroup of your design, than you do have dependent variables. Another way of looking at it is how robust the analysis would be to violations of normality, and Tabachnik and Fiddle argue that if you've got at least 20 observations in each cell of the design, then it should be fairly robust to that. But that is a separate issue to power. So the ability of the test to detect a significant difference between your groups or conditions, if it really exists. And so even if you've got 20 participants, if you've got a lot of subgroups in the analysis, so multiple independent variables with multiple levels, only having 20 people in each of those subgroups might not be enough for you to have adequate power. So there are a lot of issues around determining sample size and what adequate sample size is for MANOVA. But really you need to have a decent amount of data so that your MANOVA is robust to things like not multicollinearity, sorry, normal distribution issues, but also to you need equal numbers in each subgroup or each group to avoid the pitfalls of the equality of error covariances. If you have a between groups element, you'll also have to look at things like equality of homogeneity, equality of error variances or homogeneity of error variances. That's only if you have a between groups element, and that's only when you're breaking your effects down to look at each dependent variable separately. And that's the same for sphericity if you're not taking the doubly multivariate approach. Well, I'll come on to all of those a bit later. So we need to return then to start with to this idea of sample size, because it's a huge issue with MANOVA, and there's a lot of misuse of MANOVA, and people can try and get away with all sorts of issues. And one of the issues is that it's actually quite hard to calculate sample size for MANOVA. So in Julie Pallant, she has some suggestions which would likely result in severely underpowered analysis. It would run, but unless that you're expecting to identify a really strong, massive difference between your groups, you might not be able to detect it, and so on. So one of the best things to do is to actually try and calculate sample size using a sample size or power calculator, such as G-Power. So G-Power, and there's a link here to it, and a useful paper that talks through, gives you an example of doing that. But also there's another sample size calculator, which if you've got really complicated designs might be something to look at, called Glimpse. And again, there's a link to the calculator itself, but also a paper, the manual, that talks you through a lot of these issues. The argument is that you'll need to produce a sample size estimate that would be required to detect different effects in your analysis. So if you've only got a one-way between groups MANOVA, then that will be fairly straightforward. But if you've got a two-way between groups MANOVA, and the thing you're really interested in is the interaction effect, that's the thing that you should estimate your sample size for. It's likely to be larger that's required than just looking at the individual main effects and so on. And so it can get complicated very quickly. So I would have a look at this. If in doubt, an absolute minimum I'd say would be 20 participants per group, or per subgroup if you've got more than two dependent variables. But really key is aiming for equal numbers. So if you've got massively different numbers in each of your groups, this will cause a problem. You have to really thoroughly check your assessment, your data assumption checks in that scenario. Okay, so another note then. What would we expect to see? I've just been talking about different effects. So if we had a simple design example would be a one-way MANOVA, and in the example provided there, it's a one-way between groups MANOVA. What it does is it provides a multivariate main effect. So when you look at all your dependent variables together, is there a difference between your groups? And if you find a difference, you can then break it down and look at each of your dependent variables in turn. So let's have a look at this example. So going back to the paper, so if I scroll down, we can see the instruments and information about kind of how it was developed. That's the first part of the paper. So the second part is here. So we know that it was a one-way between groups MANOVA was performed. We wanted to see whether there were a difference on our 4 dependent variables between students in their first, second or third year. I checked all of the assumptions, and luckily we didn't have any particular problems. Now I say luckily because if you look at the sample size in each of our groups, so data was collected in semester 2 of year 1 for people in the first year of study, semester 2 of year 2 for the people in the second year of study, and semester 2 of the third year for people in the third year of study. But what you can see is we've got quite different sample sizes. So 108 in our first group, 85 in our second group, and 51 in our first group. So if when I was checking the data, we had violated some of these assumptions, then we would have a problem. Probably not so much in terms of normality, because we've got more than 20 observations in each group. So that's a good sign. It'd be fairly robust to those sorts of issues. But if I had violated that, the test of equality of error covariance matrices, this would be a problem. I'd have to follow it up. I'd have to explore, which group had the most variance and why. But I will talk a little bit more about that later. So what we can see here is that we've got our first multivariate main effect. So what we can tell here is that there was a significant main effect of study year. So that was the main effect when we consider all of these things together, all of those 4 dependent variables together. Actually, yes, overall, on evidence-based practice profiles, this kind of composite, big first analysis, which we call the multivariate main effect, there was an effect of study year. So when we consider all of these 4 dependent variables together, there were differences on the first, the second, and the third year students. Okay, but as I said, it's an omnibus test, so we don't know where that is. We'd need to go and look at that further. But there was a difference, and it was statistically significant. So the next thing you'd have to do is break that down further. And you would have to look at separately on the practice subscale, which is the frequency of practice. Again, there was a statistically significant result. On the retrieval and reviewing of evidence, there was a statistically significant result. But on 2 of the dependent variables, when they were considered separately, so attitudes and sharing and applying, they were not statistically significant. Now this one's obviously non-significant. It's way over 0.05. But you might be looking at this and thinking, well, hang on a minute, that value is less than 0.05. What's going on there? And that's something we'll have to come back to later. But it's because we applied something called the Bonferroni correction, because we were running multiple analyses now. There is a convention within MANOVA research to apply this correction when you start breaking things down and looking at each dependent variable separately to try and reduce the risk of making a type 1 error. Although that would have been statistically significant at a 0.05 level, when we apply this Bonferroni correction, it is no longer significant. But I'll come back to that and illustrate that in a bit more depth. But you can see that, okay, so that was the multivariate main effect here, when it considers all dependent variables together. These are the univariate effects. So when you look at the differences between the 3 groups on the 4 dependent variables separately, we still find differences on some of the variables. But at this point, we don't know where, because we've got 3 groups. It could be that they're all different from each other, or only 2 of them are. But some of them we don't find a significant difference on when we look at them separately. So these are the univariate main effects. This is the multivariate main effect. So when you've only got one independent variable, you can only ever talk about main effects, because you've only got that single independent variable that you're trying to estimate how much it influences your outcome variable, your dependent variable. But once you start getting more complex designs, and so once you start having a 2-way MANOVA or above, so 2 independent variables, 3 independent variables, and so on, it becomes more complicated. And you actually have, as well as main effects, so as well as multivariate main effect and univariate main effect, you also have something called an interaction effect. And so this is where it's similar in a way to ANOVA. The 2 independent variables in this example come together to influence, in this respect, in the first part in the multivariate effects, they come together to influence the shape of scores across your dependent variables when they're considered simultaneously. And then again, a univariate interaction effect. Well, that's when you've got, if you think back to ANOVA, when you have an interaction between the two independent variables and they produce a different score on your outcome. So actually, as soon as you start having more than one independent variable, you also have interaction effects that you have to interpret. And then you have to break it down further. If you find an interaction effect, then you'll have to think about looking at things like simple effects. So if you're not sure about what interaction and simple effects are, go back to that MANOVA lecture where I talked through it in detail. And the same thing really applies here. But let's just look at the second example. So this is the paper which talks through a repeated measures MANOVA. So each person has taken part in every cell of the design, so every condition, and they have two independent variables. And so in the first study, they also have several studies, I should say. So the first study, they talk about the task, they outline it, what they needed to do. And so here we are. So we have the two experiments. So multisensory target was where they presented a sound, a tone, and an LED light, and sometimes that was they were congruent and sometimes they weren't, and so you had a target stimuli that you had to reply to, and you had to say whether you thought that they were congruent or not, or so on. And if they were congruent, you had to press with your foot one pedal, and if they were incongruent, you had to press the other foot pedal. But to make things confusing, they had a distractor task, which was a similar layout, a tone and a colour, LED light. And so sometimes they were, both sets of stimuli were congruent, sometimes they were incongruent, and so on. And they wanted to explore the effect of this. So when you have a multisensory distractor, in your kind of your field of vision to the left of or to the right of your field of vision, not in the center, you know, how do you react to your target stimuli? You know, how does that distractor work? And so this is the type of analysis that they've done. They talk about the sample size. This is the setup, so it gives you an idea of what was going on. The experiment consisted of a 3x3 repeated measures design. But in this case, they also had two dependent variables. So this is why they were doing a repeated measures MANOVA. They had response times and error rates. Okay, so you had two dependent variables and they wanted to look at them together. So as we come down to the results, we've got some background information here. We've got the mean reaction time here, and so we can see that we have they've performed a 3x3 multivariate analysis of variance. Now we'll come on to what that means in a moment. So the MANOVA revealed a significant main effect of visual distractor feature congruency. So that's the multivariate main effect. So that was statistically significant. And there's also a multivariate main effect of the auditory distractor feature. But there was no significant interaction between the two. So what they've argued is that that suggests that the two sensory distractor features were processed independently. So these things were, so we can break it down, and we would look at this main effect further, and we would look at whether there was a significant difference based on whether that was looking at error rates or at mean reaction times or both. And we would do the same then for the auditory condition, and we break it down to the univariate main effect of this feature, distractor feature congruency on mean reaction time and error rate. What we wouldn't try and do is look at the combination of the two, because there's nothing going on in this interaction. So this effect, because we haven't found a significant interaction, we can say that this main effect, this multivariate main effect, is not contingent on this one. Those two things are being treated separately. They don't seem to interact to influence each other. But you're starting to see now that this is the multivariate effects. the multivariate main effect of visual distractor feature, the multivariate main effect of auditory distractor feature, and that would be the multivariate interaction between the two. But as we can see here, that p-value is much larger than 0.05. There was nothing going on. So what we've got to do then is break it down further. So what they've done is they've checked it using other things. They wanted to rule out any other explanation, so they've got different types of MANOVAs here. But what they would also do is potentially break it down by each level of the distractor feature and auditory feature, compare between them. They find that still there isn't an interaction effect, and so on. So that was on the mean reaction time. So they did this on the errors as well. They've broken it down further. But it gives you an idea of actually the complexity of the results. Now this is actually quite a complex paper, but it's well worth a look. There aren't that many that talk about their approach to the analysis with MANOVA and repeated measures MANOVA as clearly as this does and in so much detail. So it's a really good example to look at, but it is still quite challenging to read and understand what's going on. But you can see then you would have a multivariate main effect, you would have a multivariate interaction effect. Now if you find something going on here, then it warrants looking at your univariate main effect and your univariate interaction effect. If you don't find an effect at the multivariate level when you're considering all your dependent variables together, then usually there's an argument that you shouldn't go any further. You shouldn't break it down any further. There are cases where that you can do that, but we'll talk about those later. So usually if it was a one-way between groups MANOVA, if you don't find a multivariate main effect, you wouldn't break it down by dependent variable and look at them separately. You just say, nah, there's nothing going on. I'll talk about the scenarios in which you could counter that argument later. So in a doubly multivariate MANOVA, we have other things. You might have main effects, you might have interaction effects, and again, multivariate and univariate levels of that. But we would handle, and it's usually if there's a time element, so repeated measurements of the same variables again and again, we would handle it in a slightly different way. So there's an example there of the paper at Unital that I showed you earlier, the two-way between groups MANOVA. Okay, so in terms of the doubly multivariate MANOVA, in a lot of instances, the way that it's reported looks very similar. You would have your multivariate main effects, interaction effects, univariate main effects and univariate interaction effects, sorry, that should say. But you would also have an effect for whatever time, usually time variable that you had included. And so it's more about how these things how the analysis is performed rather than sometimes how it's presented in the final write-up. But just to give you a sense of how it might look different, I'll show you this example here, which was the example that was on the previous slide, the previous slide about different research designs. So if we look at this, what we've got is this example. They had two different groups of participants, and they had time at different points of the intervention, and they also had a number of measures that they were doing. So what they said they did is a doubly two-way multivariate repeated measures MANOVA. So this is where they've got the time points, and they've used that to as in a slightly different way as they're running the analysis. You've got the multiple dependent variables, and then you're comparing them between groups at different time points. And so it gives you an idea of the approach that they adopted. They also talk about why they've done this. So they took a kind of two-step approach and why they've done that. So this is quite a detailed study. The participants were randomly assigned and so on to different intervention groups. And you can see that we've got the measures. So we've got the physical exercise in the CBT group, that we've got the different primary outcome measures here, and then these all administered at different points in the intervention. And so what they've done is they've treated time, this variable here on the left, they've treated that as in a slightly different way in a doubly multivariate MANOVA. And then they've got some of their results here. Okay, so I would have a read through it. You've got a sense of what they've done, how they've followed up their effects using separate ANOVAs and so on. But you'll need time, I think, and a cup of tea to sit down and read through that. But it gives you an idea. Doubly multivariate MANOVAs are things that are becoming more commonly used, but they aren't used that often. So there's still a lack of guidance on how to do them well. Okay, so how does it work? Now, in some of the other lectures, what I've done is I've gone through, I've kind of decomposed the approach into some of the key formulae that are used and how they've used those formulae to calculate the results. I'm not going to do that here because MANOVA, there are so many steps to running it, calculating it by hand. If you wanted to do it by hand, that it would take a prohibitively long time. Part of the MANOVA actually are the separate ANOVAs for each dependent variable, and they function in exactly the way that we've described in your ANOVA lecture previously. But what MANOVA ultimately does is it is an extension of ANOVA, and it apportions variance into different sources. So in the same way that ANOVA does in the context of an ANOVA or in the context of regression, it portions up variance in an outcome to systematic sources, so things that we can attribute to differences between our groups of conditions, and then sources of variance that we're unsure of or that are due to error, so variances that are attributable to differences in the scores within a group. Within a condition. So it does that in the same way or in a similar way, but there are more steps to it, if that makes sense. So I'm not going to go into too much detail on that. If you want to explore that, I would read the chapter in the MANOVA chapter in Tabachnik and Fiddle's book. They provide the essential formulae that are used, and they talk through how they're calculated, and they give some examples as well. So if you want to look at that and how it is done by hand, there are a lot of similarities with ANOVA, but there are differences too, and that's the text I would recommend you look at for that. So, okay, when I was looking at one of those previous examples, you might have noticed I hovered over something called Peli's trace, which test statistic. And I said, I'll come back to that. So, as with anything, MANOVA, it's not as straightforward as just being given a one F ratio. What happens is that SPSS produces a number of versions of F, and you have to choose between them based on your knowledge of the context of the research, how the data is behaving, and so on. You have to choose between those and interpret which one you think is the most appropriate for that scenario. And so actually when you run your analysis for the multivariate main effects, you will have 4 types of F ratio that you have to choose between. So you would have Peli's trace, which is typically denoted with an italicized V, Wilks lambda, which is typically denoted by an italicized lambda sign, Hotelling's trace, which is usually denoted by an italics T squared, and Roy's largest root, which is, I think it's the omega max symbol that you can choose. If in doubt, just write the name of the test statistic, that's absolutely fine as well. So each of these represents a different way of calculating F, which, as we know, is a ratio of explained over unexplained variance in our outcome. And they correct for different issues with data. So if you want to look at exactly how each of these are calculated, if that's how you best learn, and also to understand what each of these are, I've put a link to quite an interesting paper by the NCSS at the bottom of this page, so it's worth having a look at it. But each of these really should be used in different situations. If you have between groups MANOVA and you only have two groups, so you've only got one IV and that IV only has two levels, then you can just use the Hotelling's trace. That's fine. But typically we have either more levels to our IV than that, or we have more than one IV. So your choice will usually be between the Wilks lambda or the Peli's trace. If you have a reasonable sample size, and if you've got equal numbers in your groups, you don't have any issues with non-normality and so on, then actually the Wilks lambda is absolutely fine to report. It is the one that's most commonly used, so there's an appeal to using that because people are used to seeing it in terms of MANOVA. However, if you have unequal groups, and particularly if you have issues with normality with these unequal groups, then Peli's trace is more robust and you should use it. If in doubt, I would use Peli's trace. It might be less commonly used, but it's more robust, and there are arguments around that. You can look at things like Tabachnik and Fiddle and so on for support for that. I would say that unless you've got a very specific reason to use them, that otherwise you should just ignore Hotelling's trace and ignore Roy's Lodge's route, because there are very few circumstances in which those two really make sense to use, why you prioritise them. So really, when you're looking at your output, you'll be making a decision between Wilks lambda and Peli's trace. If you have unequal groups and you're in any doubt, just use Peli's trace. In other circumstances, you can use Wilks lambda. Okay, so we're going to try and think about this in a bit more depth in terms of what we mean by kind of effects and designs and so on. So I've been talking about MANOVAs as between groups MANOVA, repeated measures MANOVA, and mixed methods MANOVA, and so on. You may see people refer to them as independent groups, unrelated groups, or related groups for the repeated measures, and so on, but they essentially mean the same thing. So in terms of the IV, what we've got is, in this example, if they were between groups, we've got one IV with gender with two levels. You'd either, in this example, be self-identify as male or female. This is just an example. Or you've got a second IV, and the point at which people have been, a snapshot then of when this data has been collected, they're either in the young group, the middle-aged group, or the old group. Again, this is just an example. So in this example, when you have the multivariate main effect, it's where you look at a main effect of gender ignoring age on your dependent variables all grouped together. That's a multivariate main effect. The multivariate main effect of age would be where you look at differences, if there's a difference between young, middle-aged and older participants, regardless of their gender. So you ignore the effects of the other variable. And so that would be an example of the main effects. And each person would appear in only one cell of the design. So what I mean by cell is they'd either be male young, male middle-aged, male old, or female young, female middle-aged, or female old. They wouldn't appear in more than one subgroup of the design. So this is fully between groups. And each of those independent variables is between groups in nature. So you'll see people refer to it as the between subjects effect as well. In repeated measures, actually what we have is that each individual appears in multiple levels of the IV. So they appear in each level of each IV if it's truly repeated measures. So you have, for example, your first IV might be test period. So before the treatment or after the treatment, pre or post, you would appear in both of those levels if you're going to be included in the analysis. So you'd have all of your measurements taken before, and all of your measurements taken afterwards. So you would have all of your measurements taken before and all of your measurements taken afterwards as well. The second IV might be different individual differences as a that we've got measures of personality, memory, and verbal reasoning. Again, if it was fully repeated measures, then you would have completed each of those questionnaires. So we would have kind of psychometrics as a second IV, and in the similar to between groups MANOVA, what we'd be looking at as a main effect would be the main effect of test period, regardless of psychometrics. That would be the main effect of test period, or the main effect of psychometrics, regardless of time period. And so that would be the main effect of psychometrics. And if it was a multivariate main effect, it would be looking at your 3 dependent variables, whatever they are, all together. Okay, so maybe your 3 dependent variables are aspects of well-being. So in mixed designs, you would have a mixture of the two. You would have one IV which was between repeated measures, for example. So in this case, and repeated measures, you would also see people call about within subjects effects. That's a repeated measures effect, or a repeated measures variable. So the first IV would be test period before and after the treatment, whatever that was, and you would have each person would take part in both of those levels of the IV. The other group, the other variable would be your independent groups or your between subjects variable, and that might be the age at which this study took place. So young, middle-aged, or old. You'd either appear in one of those groups or the other, but not all 3. Whereas your first variable, you would appear in both levels of the IV, so pre and post treatment. And you would look at that again. You'd have the main effect looking at test period, ignoring age level, and the other main effect of age, ignoring test period. And you'd look at those as a multivariate main effect when they're all together. Let's imagine then that we're looking at a factorial MANOVA. So factorial tells us that there's more than one independent variable. That's how you might see it reported. And MANOVA tells us that we've got more than one dependent variable that we're looking at simultaneously. So in this example, we have our 3 dependent variables, the different forms of reasoning. So we have verbal reasoning, quantitative reasoning, and abstract reasoning. So those are our dependent variables. So overall, they come together as this sort of maybe measure of intelligence, then some form of measure of intelligence overall, when they're considered simultaneously. Our independent variables are that we have gender and age, and in this case we can see that it's a between groups analysis, because we have our first variable, gender. It has 2 levels. Someone either is self-identified as male or female in this example, and age, again, 2 levels. Someone is either being put into the young group or the old group. So these are just just illustrations then. So what our research question might be is looking at, whether gender or age, what are the differences between males and females and young versus older individuals on intelligence overall. But we might also be interested in things like how gender and age interact. So, and we'll come on to that in a moment. But in this, we'll be looking at, say, the main effect. So what we'd be really interested in as a main effect is how gender, regardless of whether someone is young or old in this experiment, in this study, do we see a difference between males and females on our DVs together, if we're considering them as some sort of, representing intelligence? And then if we do and we break that down further, do we see a difference between males and females, regardless of their age, on verbal, on quantitative, and on abstract reasoning? And then the main the main effect for the age variable would be, do we see a difference between young versus older individuals on this intelligence, new dependent variable created from all three of these variables. Overall, regardless of whether someone is male or female, and then breaking it down, do we see a difference between young versus older individuals on verbal, quantitative, and abstract reasoning? And so that's what these arrows represent. So they are the main effects of gender on verbal reasoning, on quantitative reasoning, and on abstract reasoning, and then the main effects of age on verbal, on quantitative, and abstract reasoning, where we aren't looking at the degree to which these things influence each other. The main effects are looking at gender, ignoring age, and looking at age, ignoring gender. In terms of the interaction effect, what we would be saying is actually that there is something going on, that there is a difference between potentially males and females on verbal reasoning, but only for young individuals. Or there's a difference between males and females on abstract reasoning, but only for the older adults. That would be an example of an interaction. And actually what we could do is test that. So we could look at, it may appear from our analysis there's something going on, a difference in the mean scores between males and females in the young group but not the old group, or so on. And we could test that directly. And that is actually what is called a simple effect. And that's where you look at the difference between two levels of one of the IV on each level of the other IV, so separating them out. So another example might be that we find a difference between young and older adults on the quantitative reasoning, but only for males, or something like that. So that would be an interaction where we can't just look at gender separately, we can't just look at age separately, because they interact with each other. The effects on verbal or quantitative or abstract reasoning of gender are contingent on age or vice versa. Okay, and so when you have an interaction effect in your analysis, it becomes a lot more complicated in terms of any main effects. So in this example, if we found that we had an interaction effect between gender and age, we should place a lot more weight and focus in our reporting of our results on that interaction than the main effects, because we know that the main effect of gender is misleading. It's actually contingent on someone's age, or vice versa, depending on what we found in our results kind of thing. So when you do find an interaction effect between two IVs, you have to be very careful about what you say about any main effects you've already identified. So your interaction effect should be the primary focus. Okay, so I've been talking a lot about effects, but there's another way of talking about this as well. So as part of a MANOVA, obviously, and some of the examples I've been showing you, I've been saying, oh, this is this provides, a statistically significant difference on the multivariate main effect, or, on the univariate effect, the between the groups, there's a difference. But as I've said before with ANOVA, and with regression or anything like that, it's not just about whether it's statistically significant, because that is tied to the size of a sample. So if you've got a massive sample, you could identify the tiniest differences between groups. It would be like being able to detect something with the naked eye versus detecting something with a microscope. You'd be able to see something a lot clearer in a microscope, even if it was tiny in comparison, than seeing something just with the naked eye. So the microscope would be if you had an example of 10,000 participants, you could detect the tiniest differences between your groups, but that doesn't necessarily mean it's actually useful. The difference may be actually so slight that in practice, it doesn't really equate to anything. It wouldn't really allow you to apply the finding in any way that would make a difference. And so this is where we should be thinking about effect size. And so effect size is something that I've sort of talked about in regression in different ways, but also in ANOVA in different ways. And the effect size that is produced as part of MANOVA is the effect size that you see quoted for when it produces effect sizes for ANOVA. So the one that you'll often see the SPSS produces is the partial eta squared or eta squared, which is this kind of funny looking n with a p subscript and a squared superscript. And so that's just one type of effect size. In practice, there's a preference typically in the literature for Cohen's d. It seemed to be more robust. And so there are things you can do. There are calculators out there that would allow you to change a partial eta squared into a Cohen's d if you so wanted. But you should report at least one of these with your results. And as I said, the one that SPSS produces is partial eta squared. So we can see from here what would be classed as a small difference, what would be classed as a medium difference, and what would be classed as a large difference. What you'll notice if you look at some of the different example papers that I've talked through here, some use different approaches, some don't actually refer to an effect size, which is less typical now. But if we have a look at the Jensen et al. Paper, you'll see that they use partial eta squared. So I'll just show you that now. And so we can see here that they've reported for the multivariate main effect for the visual distractor, they have reported that it is statistically significant. But they've actually identified a very strong relationship between the variables. So if we looked at our example here, they actually I've identified a massive effect size for their main effects, and then still a large but considerably smaller effect for their interaction, but that still wasn't statistically significant. Effect size also can give you an idea of the relative importance and how consistent an effect might be over repeated sampling. So we would always report effect size, we should do, with our p-value. Now, prior to doing this, one of the things that I talked about in terms of the example paper is that I applied something called the Bonferroni correction in the paper to try and correct for type 1 error, so or the family-wise error, as it's called, the long-run type 1 error. So this is where every time you do an analysis, we have a threshold of deciding that something is statistically significant if the p-value is calculated to be 0.05 or smaller. So that means if we did this 100 times, 5 times out of 100 we would make a mistake. We would say that something is going on when it isn't, and that is a type 1 error. So that equates to a 1 in 20 chance each time we do an analysis. Now, the issue is that as soon as you start doing multiple testing, so we do a significance test for each of our 3 or 4 dependent variables, that margin for error is actually cumulative. So it's additive. It kind of clumps together, and actually what it can mean is that simply because you're doing lots of analyses, you're heightening the chance of finding something statistically significant just because you're looking more, if that makes sense. And so one of the arguments is that we should be doing something to try and correct for that. Now, in approaches like regression, it's a bit hypocritical because we usually use the initial model statistical significance as the cap for that type 1 error, so that when you're looking at the individual significance for your predictor variables, if you've got multiple predictors in your model, we don't usually apply the Bonferroni correction, but it has become conventional to apply it to MANOVA, even though actually the argument is that by doing this multivariate main effect, we should be kind of seeing if there is something overall to the difference between the groups, and that should act like a kind of cap for our long-run family-wise error rate. But actually you'll find that conventions mean that there's an argument that you should be applying the Bonferroni correction when you are looking at the individual results for each of your dependent variables. Now it becomes the water becomes very muddy at this point, because it's not clear what we mean by a family of tests. Do you mean every single analysis you've run in a paper? Do you mean only the analysis, so you would apply the Bonferroni correction to the the 4 comparisons you're doing as part of your univariate analysis, and then you would apply the correction afresh when you come to do any pairwise comparisons, or should you include all of them together? There are a lot of issues with understanding that, and if you Google Bonferroni correction and MANOVA and controversies, then you'll probably find some papers that talk about this, and the fact that the Bonferroni correction is incredibly conservative, so you could end up with a situation where you have an overall multivariate statistically significant effect, and when you break it down, apply your Bonferroni correction and look at each dependent variable separately, you don't find anything. And so that's usually because of a power issue, because the Bonferroni correction is so conservative. And so there are some alternatives if you still want to try and correct for it, if you still feel uncomfortable by not applying any correction, then there are a couple of alternatives, and here are some papers, or here are some blog posts that talk about 2 approaches to doing this. The whole Bonferroni correction, which is something that I have used in the past, I found it to have a good balance between being conservative but not too conservative that you just obliterate your chances of finding anything statistically significant. So it gets a bit of a balance between type 1 and type 2 error. So type 2 is a false negative, type 1 is a false positive. Another approach is the false discovery rate, or the false detection rate, which is used a lot in other bio or kind of ecology fields, where there are often cases where you're doing dozens of significance tests within the same paper. And that's another approach to identifying what should be classed as a genuine significant difference or significant relationship, and a spurious one purely because of the number of analyses you've conducted. So I would have a look at both of those options. And I think if you were going to apply the Bonferroni correction and you have a lot of comparisons that you want to make, then actually the whole Bonferroni correction might be the best thing to use instead. So in the example paper, let me just take you to that, where I encountered a number of issues this when I was doing the analysis. So actually what we had the 3 groups, as you've seen, that they were unequal in size. Luckily, we didn't actually have any issues with the Box's test, which is the test of equality of covariance matrices, error covariance matrices, and the normality tests. There was nothing concerning there, and so it meant that actually we could kind of proceed with using things like Wilks lambda to look at the differences between the groups, the 3 different year groups, on our 4 dependent variables, and there was nothing too worrying to look at from the assumption checking. What we found is that there was the overall statistically significant result. There were univariate main effects for some of the variables. Because it was only a one-way ANOVA, I didn't have any interaction effects. But if you look at the paper, what we do is, because we find a significant difference on some of our dependent variables between the 3 groups, we do follow-up simple main effects analysis, which is where we look at the difference between some of the between the years on the different dependent variables and compare between them. So let me just show you that. So as you can see, we said that we found overall that there was an effect of year of study on the dependent variables. So that warranted us to kind of look at each dependent variable separately. We found a difference on the frequency of practice subscale, and we found one on the retrieval and reviewing evidence subscale, but not on the other 2 subscales. So at this point, we stop checking any further on that. But on these 2 variables, all we know now is that there is a difference somewhere between the 3 year groups, but not where. So what we did is we followed that up with a post hoc comparison, where we compared each group with each other group on each dependent variable, and in kind of separate pairwise comparisons. So what we can see here is we actually broke it up in 2 ways. So we applied Bonferroni correction to the first set of comparisons, which was the 4 univariate tests. So we we class that as a family of test statistics. So what that means is we were going to run 4 analyses, therefore we had to take our usual cutoff of 0.05, divide it by 4, and that gives us our new p-value. And that's the level at which it'll have to be 0.013 or below if we're going to say that it's statistically significant. So you can see that obviously these two were at that level statistically significant. The attitude was nowhere near statistically significant, but actually applying this Bonferroni correction meant that the final effect here on sharing and applying evidence subscale went from initially being statistically significant to not. So you can see the impact here. What we're saying is this one is a spurious finding, and so we don't look into that any further. What we did then was that, well, we wanted to compare, for each of these variables, we wanted to compare, do pairwise comparisons for each year with every other year. And so we've got these numbers of comparisons that we have to make. So 1 and 3, and years 2 and 3 on the practice subscale. So what we've actually done then is class this as a new family of comparisons. So we've then started from 0.05 and we've applied the Bonferroni correction afresh to and we've developed a new cutoff value of 0.17, and that's what we've used to evaluate the statistical significance of the results. So we've got a comparison between 1 and 3, and 2 and 3 on the practice subscale, and 1 and 3 and 2 and 3 on the retrieval and reviewing evidence subscale. Okay, so what we've done is we've applied the correction twice, 2 separate times. Even so, it would still be quite restrictive, and there is no agreement in the literature on what to class as a family of test statistics as such. So hopefully that gives you an idea then. So we've got lots of different effects. If it's a one-way MANOVA, then it would just be main effects you're looking at, a multivariate and then univariate main effects. As soon as you have more than one dependent variable, then you will also have interaction effects that you've got to deal with. And as you go through ever finer level of detail, so from the multivariate to the univariate, if you find that you have significant effects at these levels, then it warrants looking at it in more detail and in more depth. And so if you end up with a univariate interaction effect, so the IVs in combination influence one of the DVs when you look at them separately, together, they come together in some way, then your independent variables, that is, then you need to look at things like simple main effects. And this is where you look at each level of one of the IVs at all the other levels of the other IV separately. So you would need to do, for example, pairwise comparisons if your IV has more than 2 levels. There's also there's an example from the two-way between groups MANOVA paper that I showed you earlier by Yonatel. And they call them simple comparisons, but it's the same thing. So these simple main effects. So if you have a look at that paper, it'll give you an idea of how they go about testing them. So, as I've said, if you find a multivariate effect, you would follow up looking at the univariate effects. If you have a univariate effect that's statistically significant, then you have to kind of break it down further and so on, and interaction effects. And this is actually, once you start doing that, you're starting to get back into the territory of ANOVA. So the initial univariate analyses that the MANOVA output includes will be univariate ANOVAs. And so if you look back at that lecture where we talk about what do you do with things like interaction effects, how do we test them, the same things, the same logic applies. If you don't have, if you've got lots and lots and lots of comparisons that you have to do, then it may be that you make the argument about descriptive statistics or profile plots. If you have very clear sets of hypotheses about specific differences between specific subgroups, then perhaps you'll use planned contrasts in some way. Or you could have post hoc testing, and that might involve testing of simple effects. So the same thing as with ANOVA, if you wanted to try and display the sorts of interaction effects that you identify, then I think line graphs are probably the best way to do that. And there are some options with the as you're running through the MANOVA to get it to produce some plots for you. There's a useful chapter in here by Cohen about displaying complex interactions and also about what ordinal and disordinal interactions are. And this is really important for things like MANOVA. The type of interaction you expect between your variables influences how much data you need to have to find it. So it can become very complicated very quickly. So an ordinal interaction is where it changes the strength of the relationship between the variables. A disordinal interaction is where it might change the direction and where you get lines that cross over each other on a graph. And if you need less data to detect a disordinal interaction than you do an ordinal interaction. So as I said, it can get complicated very quickly. So this is an example that we've taken from another paper where we had two different curricula. We were using the same measure of evidence-based practice, but in this case, this is just one for one of the subscales. But what we've got here is the attitude subscale, I think it was, and we've got people on two different curricula that were running side by side. The one was where research methods was taught on a modular basis, and the other was where research methods was embedded into the other taught sessions without a module in its own right. And so we wanted to explore the impact this has, and what we found was a disorderly interaction. So the lines kind of cross over at these two key points. And that was in the second year of study. There was something going on that changes the way that people kind of feel about evidence-based practice. In the modular, people felt a lot more comfortable, but actually this is because potentially of where their practice was coming. They'd actually gone out and done some of their placement at this point. The spiral, this was before they'd gone out into practice, and they were about to do some exams are about to go out on practice, and actually see that they're feeling potentially more anxious and as a result more negative about evidence-based practice than they were in points 1 and 3. And so you can see this kind of crossover between the two, and you can see also how useful a graph like that is to show the differences in overall kind of where things are happening at different time points in a degree. But you need to use them wisely. It can be quite easy as well to change the axis of a graph to make it look more like there's a more pronounced difference than there actually is. If you're looking at the size, don't forget the scale here. So the lowest score is only just over 4.8, and the highest score is only just over 5.6 on the scale. So of a 7-point scale. So you've got to bear it in mind and interpret them wisely. But graphs can be very good at illustrating interactions. There are different ways of producing things like simple main effects. It may be that you have to do additional follow-up ANOVAs or something like that, or you might choose to do particular post hoc comparisons using t-tests or things like that. You can actually get SPSS to produce quite complicated simple effects using a syntax document. And when we come to look at it, there's actually an example I provide as part of the two-way between groups MANOVA, and I show you the syntax that could be used to produce all of the pairwise comparisons that are needed for each level of IVs at the other levels and so on. And so actually using syntax with SPSS can save you an awful lot of time when you're doing things like this. As I said before, the issue is about, how often do we have to apply this family-wise error rate correction? So as I said before, we're not entirely sure, but what can happen is if you're doing lots and lots of explicit testing of simple effects rather than inferring things from your descriptive statistics and your plots. On the one hand, it's felt to be more kind of empirically reliable to test for them, rather than just sort of try and draw conclusions from descriptive statistics for all the usual reasons. The other issue is that because you're doing so many more tests, that you'll have to think about that family-wise error rate at some point, and how you're going to deal with it, and be really explicit about that, because there are different opinions in the literature. It's something that isn't definitely nailed down. I think it's about using your best judgment in a case, based on the context of the research, what you're planning to do with the findings. Is this just, are these the overall findings of the entire research project, or are these part of the findings that that feed in different ways? That might help you decide whether you would do explicit testing or not, and if you apply corrections or not to your simple main effects. But it is something you have to think about, and I think be upfront about as well. So what I'd like you to do now is have a look at the example walkthrough that's on Blackboard, the one way between groups MANOVA. Even if you just have a look at it, have a go at doing it, just to get a feel for what it's like to run through the analysis and how it produces the output. It produces quite a lot of output, but if you approach it in that really staged way of data assumptions that we'll be looking through in a moment, and then interpreting the multivariate effects, then the univariate effects, and then breaking it down further if you have to. And just it'll give you a sense of what everything in the output can tell you. So just have a go at that, pause this video, and then when you've done that, come back and have a look at the common help scenarios and how to manage them. Okay, so I'm going to assume that you've had a go at that then. So I'm going to talk through some of the common issues, and I've encountered them before. And some of them are kind of more sort of related to research design. Some of them, you have to plan for, and you try and avoid using a research design where you can. Sometimes you just don't know until you've actually got the data in front of you. Some things are more easy to deal with than others, and so we'll look at that now. So one of the first things is about, your groups are really unbalanced. As I said, this is a kind of research design and data collection issue. If at all possible, you should be trying to recruit equally to the different groups in your design. So it's mainly when it's a between groups variable that this is an issue. But sometimes there will only be so many people that you can recruit from one group. Quite often, for example, if you're recruiting psychology students and you're interested in gender, you'll tend to see fewer male participants taking part, fewer people of non-binary gender or transgender, and but more female, self-identified females taking part, for example. So maybe that you know going in, you're not going to be able to recruit necessarily equal numbers. And so it's more problematic when you have unequal numbers, but it's not impossible to do a MANOVA, as you've seen from the example paper I've shown you. What it means is that if you violate any of the assumptions as you're doing your data checking, it can become an enormous problem with the MANOVA, and you may have to reconsider it as a type of analysis. It's not that in itself isn't an issue. You'd say that you were seeking to do a MANOVA to start with. The data didn't support that kind of analysis, therefore you've broken it down. Perhaps you've broken it down into one-way non-parametric ANOVAs, or there are other options out there that you could use as an alternative, but there isn't anything that's the direct non-parametric equivalent of a MANOVA per se. So particularly if you've got unbalanced groups, so that's where you've got more people in some groups than the others, these issues of the data doesn't look normally distributed, you've got some multivariate outliers going on, your dependent variables are so highly correlated, or they're not correlated at all, it's a bit of a tricky ground. So this is part of kind of the first part of data assumption checking. So MANOVA works really well when you've got dependent variables that are kind of weakly up to moderately correlated with each other, and ideally that they have, the really good case scenario, they kind of have a negative correlation with each other. But it can work. It can just reduce power if you've got moderately positively correlated variables, but that's okay. What isn't okay is once you start getting really strong correlations between your outcome variables, your dependent variables, MANOVA, it massively reduces the power of MANOVA and it can produce spurious effects. So there are different ways of checking that, and hopefully you've got a sense of that from the walkthrough. But some of the procedures you'll use are actually the ones that you've encountered when you've done regression. So there are ways of checking how much your variables overlap with each other. You can check correlations between the dependent variables to see how strongly correlated they are and so on. And if you find that they are very strongly correlated, there are a couple of things you can do. One of them is that you split your analysis down, and rather than looking at all your dependent variables together, you look at them separately using separate MANOVAs. Another alternative may be that there is some way of creating kind of a composite score across the two variables that are a problem, or just dropping one of the variables from the analysis and looking at the others. If you've got more than 3 dependent variables, you can still look at those ones with MANOVA and look at the other ones separately, or so on. So there's a few things you can do if you've got really highly correlated variables. If they're not correlated at all, then that as well is a problem, and that suggests that you should just do separate MANOVAs, for example. So there are things that you need to check for as you've got your data, that will help you with that. The normal distribution, this becomes an issue when you've got unequal group sizes. And so that's where you've got huge differences between the one group and the other two. But Tabachnik and Fiddle argue that if you've got at least 20 observations per cell, so 20 people in your smallest group, and the others have got 20 or more, then it should be fairly robust to that. It should be able to handle it. And if you use Peli's trace as well, that'll help you get around some of those issues. Okay, so the next issue is about some of the other tests. So the Box's test will be produced as part of any MANOVA, so one way or more. The Levine's test is only produced as part of the univariate analyses for between groups variables, and the Mauchly's test is specific to repeated measures ANOVAs, univariate follow-ups. Now that can be an issue, particularly if you've got something like time as one of your variables, so before, during, and after an intervention, which is why you would use the doubly multivariate approach. It avoids the whole of the Mauchly's test assumptions, so you can just ignore that rather than doing it any other way. But these are all things that you have to check. Again, once you've got the data and you're looking at it, the Box's test, if you have equal numbers of people in each group, in each cell of your design, you can ignore it. It is incredibly sensitive. It will say that there's something going on when actually there isn't, if you have equal cell sizes. So you have a balanced design, it's called. As soon as you have unequal numbers in each of your groups, you have to pay a lot more attention to the variable. The issue is that if the biggest variance in your data is associated with the smallest group, it will create a spurious difference. It will make it look like the means of the groups are different. It's not the means, it's actually to do more with the spread outness. Okay, so moving on to the last kind of couple of points, which is more about what do I do in the case of when you're actually interpreting the results of the MANOVA itself. One of the things that we've already discussed is about this interaction effect. Now it depends. So if you basically the rules are that if you identify an interaction effect between two variables, for example, it could be more if you've got more than two independent variables, then you should interpret that interaction effect. You would report the main effects, but don't go any further in interpreting them, because the main effects are conditional. They're contingent on each other, so the interaction effect. If you have an interaction effect, but you've got multiple independent variables, and the interaction effect doesn't include one of your IVs, then it would be safe to interpret the main effects of that IV because it appears to be separate so that you can talk about it on its own. You don't have to talk about it as being contingent on something else. So if an interaction effect, if you find it statistically significant, then you can't talk about the main effects that interaction effect relates to in the same way, because they are contingent on each other, they are not independent. And so that's what you've got to do with an interaction effect. What can happen sometimes is you end up with a significant multivariate effect. One situation is you end up with a significant multivariate effect, but no significant univariate effects. That is probably to do with power. So that's something to bear in mind. It could also be, if you've got a significant multivariate effect, if you haven't got a significant multivariate effect, sometimes that's to do with power as well, but it could also be because of more to do with the relationship between the dependent variables, and it may mean that it doesn't make sense to consider them together. So you've got to be really clear about why you're considering your dependent variables simultaneously as you are, or whether actually it just makes more sense to look at them separately. Some people will argue that if you don't have a significant multivariate effect, then you should not go any further in the interpretation of any other effects. Sometimes you're running the MANOVA to see if they do come together in a kind of theoretical, in a way that makes sense. And so you might take it as evidence that actually these things don't fit well together, and therefore you interpret the univariate effect. I think you've just got to be really clear and be prepared for some pushback and some critiquing, either approach you take. If you find yourself in that situation, it may be better that actually you run you double check all of your data assumptions, you think carefully about how your dependent variables are theoretically related to each other, and if they really are theoretically related to each other, and then you may need to make the argument that you look at them separately rather than all together. So that's a sticky point. I think it's contentious either way, but I have seen it approached in multiple ways, that kind of issue. So that's really about kind of probing the findings and what you would do. So in one example, in another piece of research that was actually using the same questionnaire, but for the original questionnaire that was developed for use with qualified staff, we wanted to explore the evidence-based practice profiles of staff who were employed in the US and the UK and across different areas. So we had academic staff and practice-based staff in nursing, and we were exploring, what kind of patterns we saw in profiles. Actually, as we started to do that, we realised, doing the data assumption checking, we had unbalanced groups because of the different sizes of practice-based staff in relation to academic staff and so on. So we had unbalanced groups, and as I started to do the data assumption checking, we started to realise that actually we had violated quite a few of the assumptions, and some were more serious than others. And the one that was the most serious was the boxes test. It was statistically significant, and because we had unequal groups, it means you have to look into that in more detail. And what we actually found was that essentially the smallest group of participants in the research, actually their scores had the largest variance, that's when it becomes problematic. And so what we had to do is we had to look at alternatives. There was no way. We tried transformations. It didn't improve the situation. And so what we had to do was explore non-parametric alternatives, because we had also violated things like the assumption of normality when we were looking at all of them on balance. So we wanted to use a non-parametric test. Unfortunately, there's no direct equivalent of a MANOVA or a two-way MANOVA. So what we had to do is break it down into a series of effects and look at them with non-parametric, one-way non-parametric alternatives, and then break it down further into looking at simple effects and so on. So even in the worst case scenario, in that respect, when we couldn't use the MANOVA, there were alternatives. But if you were reporting that, you would say that you'd been intending to use the MANOVA, but actually the data didn't support it, and therefore you had to take an alternative approach. And that shows that you've thought about the issue, and you've been clear and transparent about your decision making. So writing up, the main thing is to know kind of your hypothesis or hypotheses really. What are you aiming to look at? What do you want to know from it? And why that's really important is because of things like sample size calculations. If you're only interested in the main effects, then you would collect enough data to test the main effects. If the interaction you've got no interest in it whatsoever for kind of theoretical reasons, then that would be an argument not to focus on it for trying to judge the sample size required. But if actually the interaction effect is the thing that you are really interested in, you're not really too bothered about the main effects in your analysis, then conversely, you would use the interaction effect to base your decision on things like sample size, as usually it requires a lot more data for you to be able to establish an interaction effect than main effects. So knowing what you're really interested in from the analysis is important. It'll help you to interrogate your output in a way that makes much more sense to you if you know what you're looking for. In terms of, by default, as with ANOVA, we are usually using, even if you specify a sort of direction for the overall approach, you're technically using a two-tailed significance test. If you're breaking it down further when you come to things like univariate tests or pairwise comparisons, then you might be using a one-way significance, one-tailed significance test. But that also has implications for things like sample size calculations, or it can do. You should be really clear about family-wise error rate, which is it's also called the long-run type 1 error rate. So no small names here, no short names. But you should be clear about that. There is an increased risk of committing a type 1 error whenever you do multiple tests within the same kind of project. So you should be clear about, as you would with any type of analysis, what you've done to control for that or adapt it, or why it's not a concern. Which approach have you taken and why? To really explore interaction effects, particularly really complicated interaction effects, then profile plots, the use of profile plots can be really helpful, but make sure that they're clear and that you're splitting up the interaction effects if you've got more than two variables at a time, for example. Make sure you're splitting those up in a way that makes sense. So have a look at that Cohen's paper of the three-way interactions to get a feel for that. And then, as with any other type of analysis you do, you have to make, to evidence any claims you make about your data, about the way the data supports the hypothesis or not, and the key points that the key decision points you've had to kind of manage as you've been going through the research process. So if you've got things like data assumption violations, the points at which you decided whether they were really problematic or not, and make sure you evidence them. So you can tell the reader which approaches to decision making you followed. So, for example, Tabachnik and Fiddle might suggest one approach. There are Julie Pallant might suggest others, or Field might suggest others. So being clear about which approach you've taken and why. As I've said, if you say you've got a statistically significant result, then report your result with significance, but also make sure you report things like effect sizes that give you that little bit more information about the results. Make sure you report your descriptive statistics and so on. And be really clear about the theory and previous empirical evidence, just to show why you're expecting to find the things you do, or that you don't find what you're expecting to, and what sense that makes of it. So in terms of APA guidelines, it's again all about clarity, about being concise, and about consistency. If you've only got a one way between groups in MANOVA, potentially you could talk about that in text. But I think actually with a MANOVA, there can be so much information that you're trying to communicate that you might need to do that using tables. The APA recommends the use of tables or figures to illustrate something which wouldn't be clear in text. So when you come to look at things like your MANOVA walkthroughs, If you look at the papers that we've given you examples of, you'll see how some of the results are presented in text and others are reported in tables and then interpreted in the text. So it's very much a judgment call. Be clear about your assumption checking and the decision you've made based on that. Don't forget to report your descriptive statistics. Sometimes people say, oh, we found a significant difference between the groups on X, and then it's like, well, what does that difference actually look like? What does it look like? And we need to see the descriptive statistics, the means and the standard deviations for each of the groups in order to make sense of that. And finally, as I've said before, make sure that you report things like your measures of effect size. If you get the option to report things like confidence intervals, they can be really useful as well. So mean difference, confidence intervals and things like that. So there is a move to including this additional information that's actually really useful and important, but has always been seen as an add-on in the past. Well, there's now a move really to make it mainstream. So things like effect sizes and confidence intervals, you should be including where you can. The strengths of MANOVA, hopefully you've got a sense of how powerful it can be, that it can help you explore conceptual or theoretically related dependent variables in different ways. It can, through a stepped process, help you interpret levels of different effect, as well as controlling for family-wise error rate in different ways. And it can be fairly robust to moderate violations of some of the data assumptions if you've got equal cell designs, a balanced design. The limitations, and therefore the misuse as well of MANOVA, is that it can get very complicated very quickly, and as a result people interpret things and report things in a way that actually isn't quite accurate or appropriate. There are lots of issues around calculating required sample size in MANOVA, and so a lot of it is about perhaps looking at different potential scenarios and creating sample size suggestions based on these different kind of scenarios in which you've got outcome variables that are weakly correlated versus moderately correlated, all those things, and then you could get a sense of the range of sample sizes that you might be needing to think about, and then make a kind of an evidence-based decision using that. There are a lot of data assumptions for MANOVA, and if you want your findings to be, for you to be able to, conclude anything from them with confidence, then you've got to check those data assumptions and be thorough and be satisfied that they've actually been met. There are lots of different opinions, as I've said, about the checking of data assumptions. Some people are far more lax than others. You need to take a professional and approach to it, and say which approach you've taken based on previous guidelines and why. And there's some debate about how to interpret the really complicated interactions. Simple main effects are useful, but you can end up with lots and lots and lots of them. So sometimes it's thinking about being really clear which differences are the ones you're interested in, and looking at those rather than every single potential combination. So know your hypothesis, as I said before. Hopefully by the end of this session then you've got an idea of what MANOVA is and when you would use it, how it works, how to deal with tricky data, and how you could communicate the findings of MANOVA in a clear and concise way. There's a good short introduction in Julie Palant's SPSS Survival Manual for MANOVA. That's probably one of the best ones for helping guiding you to actually run a MANOVA and interpret it. There's far more detail in Andy Field's book, and he has some resources here about discovering statistics. There's a link to talking about kind of procedures in multivariate analysis there by the NCSS. But if you are really focused on doing a MANOVA and you really want to understand how it works, what to do if you have problems with your data, the best thing to do is to look at Tabachnik and Fiddle's chapter. For example, in the 2014, I think that was the 6th edition. Yes, the 6th edition of Using Multivariate Statistics. It is the best most thorough guide to MANOVA really out there. Here are some of the references that we've been using today. I hope the session's been useful, but thank you.